Today's session we will take you through how to achieve or how to understand acoustics when you use glass as a barrier, because glass been widely used both for interior application and exterior application. So, it is very important to understand the basic acoustics, the definition of acoustics and noise. Before getting into generally moment we enter into glass and its acoustics, we always have myths. I would say few myths are listed here. We believe that there is a reduction of 1 dB does not make any difference, and we always believe that only 0 means it is silence, and if I use the same combination of glasses, we believe it improves better acoustics or it improves the performance, and always we will believe one based on one particular combination and we achieve a particular value that cannot be used in any other location, because if the source value is different, it means the one solution cannot be a constant for any acoustic problem because their source can be different. And in a glass you have a glass and a framing material, so glass alone cannot achieve any acoustics. Whatever the overall acoustic we need to achieve, it has to be through the glass and the system. Sum of glass means multi-layer of same thickness of glass. It does not mean the reduction that possible by one individual glass versus sum of the same thickness of glass is going to be in the same ratio of sum of. What is noise? Sound that is loud, unpleasant, unexpected, unwanted or undesired, that is called noise. What is called sound? Vibrations that are transmitted through an elastic solid or a liquid or a gas with a frequency of approximate range 20 to 20,000 hertz and capable of being detected by human organs of hearing. So, why decibel is a very important question to be understood, because our human ear is extremely, and it is an amazing system it has, because human ear can understand the threshold of hearing for a human ear is about 20 micropascal, whereas the threshold of pain it is 20 Pascal. If you convert it to a frequency, 20 Pascal is approximately at 1000 hertz frequency. What is called decibel? It is a combination or it is a ratio of a power, the frequency that is going to hit, the pressure, the intensity and the voltage. The combination of all or the ratio of all is being measured called and by an individual numbered called decibel. So, when you have a source, you have a huge range of intensity which is the loudness, and there is a medium it going to transfer, and then there is a pitch which is called the frequency pitch. There is a low frequency and there is a high frequency pitches which is going to reach you. So, this three combination is going to decide whether it is going to be a pleasant noise or it going to be a disturbance. So, the same I said. So, there is a frequency difference when you see the silent versus noisy, the way it going to reach you with the intensity, it is going to be an impact on your ears. Commonly what you can, how much you can able to withstand or where you can have what kind of level of noises, anywhere in a living space you can be at less than 40 dB, it includes your living and sleeping. So, sleeping usually suggested to be less than 35 dB. When a working station or a business offices, it can be even up to 60 to 65 dB. Anything more than 80 dB, you call it as a noisy environment, and anything more than 100 plus, it will be really a disturbance, and more than 120, it can become an unbearable. That is where if you connect it to my myth, even a 1 dB reduction at this scale, it is going to be a huge reduction, because the impact of a noise after 40 to 45 dB, the impact of noise at every 1 dB, the impact will be double. So, which you cannot bear. So, the level what you can be bearable versus not bearable is hardly 1 dB difference. So, how the sound interacts? The sound interacts when there is a source going to hit an element or an object or an layer. So, there is a part it is going to get transferred, part is going to reflected, part it is going to get diffused, which is because of the surface of your the medium it going to hit, and there can be, this all can happen based on the mass of your material, because mass again it relates to the frequency filtration process. So, when you come to glass and acoustics, you have to be very clear on two important factors, which is called your RW and STC. STC is called sound transmission class, whereas RW is called weighted sound reduction index. In both, when you wanted to measure, when you want to plot, both has very similar methodology. Only the basic difference is the frequency range and the contour, standard contour graph which we are going to plot. There is a difference in that. Whereas when you measure STC, you measure as per ASTM E413. When you go to RW, you measure as per ISO 797. Plus, when the frequency ranges for STC is at around 100 to 3150, whereas for RW it is about 125 to 4000 Hertz. What is called RW? It is an weighted sound reduction. It is a simple and a single value index which is measured in decibel. As we understood, whatever we receive on from the source to the observer side, we measure it with a single value index called decibel. In case of specific to a building, when you have a value, whether it is RW or even an STC, specifically in case of an RW, we need to be very careful based on the type of a source. Based on the type of the source, you have to understand, or you have to have an adjustment factors which is nothing but RWC or RWCTR. C, which is it's an adjustment factor which relates to a very fast high traffic, railways or airplane, where the pitch is very high, and then whereas in case of a traffic which is a slow traffic, the vehicle movement, general public disturbances or very different musics which comes under CTR. To make it clear, say for example, if you take ISO 797, it clearly gives a table what adjustment factor you have to use to achieve your RW inside a building based on the type of a source. Say for example, if a children is playing outside, you have to take your RW value and you have to apply your RATR adjustment factor to it. So that will be your final achievable or possible noise inside your building which going to come from the source. So based on the different sources, whether it is from children, domestic, whether it is a discotheque music or a different types of road traffic, whether it is slow or high, or again it is road or airways, or again in industry, what kind of disturbance that comes from an industry. So this is very important to understand. There is something called RW and there is an adjustment factor called RA and RATR, which is very specific to internal application. So this is to show you how the frequency ranges based on different STCs, when from 0 to 120, whether it is STC or RW, this is how your frequency bandwidth will be there. To understand more, if you take the lower STC ranges, say less than 30, your frequency, that lower frequency, the intensities are high, the intensities are very high in the range of 50 to 60, whereas the frequency is low. So the disturbance, the noise which is going to enter or which is going to be affecting you as an individual will be very less, the impact is very less. Moment you go above 70 and 80, you can see the intensity and the frequency impact are more or less same, and which is going to really hit you in your psychological impact. To derive these graphs, first we need to understand what is called octave bands. Octave bands is nothing but we need to understand the 1/3 values. You have to plot your graph or you have to measure your impact of any barrier, and you have to plot it in this octave bandwidth, which is nothing but the highest frequency is twice of the lowest frequency. So this is given in an ISO. So based on it, whenever you measure any material, you have to plot your graphs as per your 1/3 bandwidth, then you align it to your standard contour graph, so that to understand your STC or RW. I will take you through how to calculate after you measured something, because measurement usually cannot be done at a regular standard locations. You need a laboratory setup condition, or you need a very specific setup to measure acoustics based on from different frequencies, say from 100 or from 125 to 4000. Then you have to plot completely the graph, and then you have to assign it to a contour. So when you plot a graph, it's very important that the measurement values are very important, because your human ear ranging frequency starts from 20 to 20,000 hertz, but whereas it's become very critical when it has become 500 to 8,000 hertz. Usually that is why STC values or RW values are calculated at a frequency bandwidth of 500. So, this is a standard graph, you can plotted graph you can see for a particular STC say 52, you have an STC contour line which is drawn and there is a measurement line which is called the TL, the transmission line which is drawn. So, the methodology to do this is, first I have to measure the transmission loss. So, I have a source and I have a receiver, there is a different frequency being emitted, there is a barrier and there is a receiver. So, based on the different frequency being measured inside, the transmission loss curve being plotted from say a 125 to 3150 or even up to 4000 hertz. Once the transmission loss graph has been drawn, then I have to find my trial contour line, I have to fit the contour line into the graph. How to fit? I have some basic methodology to be followed. Usually I have to start fitting the contour mapping at 500, considering at 500 it is 0. So, when I plot it, because of the shape of the contour mapping, because of your transmission losses graph based on your different frequency in pitches, there will be ups and downs. So, there is a particular condition I have to achieve that the maximum deficiency or the distance between the transmission loss curve and your contour graph, contour line cannot be go beyond 8 dB. So, when I plot this at 0, when I assume that it is 0, then I have both the positive and negative which I have to sum it up. These two important parameters to be considered is the total deficiency cannot be greater than 32. Even in this case, if you see there is a plus 16. So, this contour line has to be further adjusted so that the maximum gap has to be 8 dB. When I plot that, considering these two criteria, then I will be able to achieve the contour and my trial. Then whatever it is at 500 is my STC value, which is the whatever value in my contour line at 500 hertz will be my STC or RW value. So, to understand how it respect to the glass, a normal float glass based on different thicknesses, whether it can be from 4 mm to 12 mm, when it is a single unit, the ranges will be from 29 to 37 dB because from 4 mm. So, every next glass thicknesses there will be improvement in your performance. Moment I laminate it, means I am going to sandwiching two glasses with a material called PVB or it can be with a Sentry. Based on the number of layers and type of bonding element I use, the ranges can be from 32 to 39 dB. The same combination for lamination, I can even use an acoustic material which is used, which can further improve the efficiency or which can further reduce the noise transferring. So, which can improve from 32 to 36, so it can reach up to even 43 dB. To further achieve, if I have to further reduce my noise level coming into my building from my source, then the next option available for me is to make a double glazing unit. In the double glazing unit, I can go for symmetric glass, asymmetric glasses, where based on the kind of thickness of glass combination I use, there can be reduction varied, or I can use a laminated glass in a double glazing format which can further increase my acoustic performance. How the acoustic glass is going to perform? It is going to perform on basically based on two important parameters. One is the thickness of the glass, which is going to be a major factor. Second one is the PVB, which is actually behaving like a dampening material. Whereas there is another option called Sentry interlayer which can further improve the acoustic performance because it is the stiffness of the material, the dampening property of the material is further enhanced, which can have a better impact on the overall acoustic. So, to recap it, so we have gone through what is called the basics of acoustics. I mean, it has to be measured in a decibel, which is a single unit for number. It varies based on the type you do or the kind of standard you refer to, whether it is to as per ISO or as per EN. So, there is two parameters called RW and STC. When you go very deep into it, the STC RW, the range will be within a deviation of 1 to 2 dB, you can derive it. It is only a matter of the standard and the frequency you take through. So, based on the source, again you have to use an adjustment factors which is called RAC and RATR. Moment you are able to understand the basic terminology, then you should be able to understand how to plot it. So, to plot it, we need to plot first the transmission loss graph, then I have to plot a contour. The maximum difference between the contour and my transmission loss has to be 8 dB. After plotting it, I have to calculate the overall deficiency, which cannot go more than 32. So, once it is done, at 500, whatever is the contour, that will become my STC value. So, specific to glass, more thicker is better because it is heavy. So, there is a less tendency to vibrate or to resonance. So, but in a single glazing, maximum available will be a 12 mm thick. In a single glaze, you can use it in an architectural application. So, maximum you can achieve is about 36 dB to 37 dB. So, further if you want to improve, you have to go into a lamination format. Again in lamination, as always, thicker is better, but here because of the benefit of the PVB or your Sentry, which behaves like an acoustic barrier, which helps you to decouple your individual glasses. So, there is 2 layer of glass and there is an PVB. So, there is and suggested to always go with an asymmetric glasses, because every thickness of the glass, because sound travels with a mass. So, every different mass behaves like a different filters. So, when you use an asymmetric glasses, the frequency, the frequency capacity to pass through will be varying. So, when you use an asymmetric glass with a PVB, so the glass 1 able to block particular frequency and the PVB, and then the glass 2 will be able to block a particular frequency or different frequencies. So, when you sum of this all, there will be a positive or there will be a better reduction. Whereas, when you do a simple lamination, you can achieve maximum is about 37 to 42 dB. When the source level is about 80 dB outside your building, and you wanted to achieve something less than 40 dB or even 35 dB, where it's in case of an hotel where you wanted to have a complete silence. I mean, complete silence here means anything less than 25 dB, it's very tough to understand. I can take in one classic example is the normal air conditioning noise, what you are used to it, which is in the range of 35 to 37 dB. So, in a hotel where you have to achieve less than 35 dB from a source of 80, so you have to reduce more than 45 dB. So, 45 dB cannot be achieved only through glass. So, glass and a system. So, when you select a glass, it better to suggest or better to take 2 or 3 dB higher RW or STC, so that even there is a possibility of loss through your system or leakages, still you will be able to achieve that 45 dB. So, to achieve anything more than 40 to 43 dB, you have to go for a double glazing unit, where you have to have the outer light laminated, or if you wanted to achieve anything more than 45-46 dB, it's suggested to have even both the lights laminated. Again, to achieve a particular STC range, you have to find that different glass thicknesses has very huge impact on your different frequency. So, again it is coming back to what is the purpose and for what source we are going to reduce it. That is where your TL graph is very important to understand. Based on your source, you have to plot your graph, and based on your source, you have to understand your contour and then derive your STC considering your source and your adjustment factors. Once we are able to understand these 3 important parameters, your RW, your adjustment factors and your source, which is very important so that you can play well within acoustics. Thank you. I hope this session will help you understanding very basics about acoustics, terminologies in acoustics, and how to understand glass and how to take it positive, how to reduce the noise transferring into your building. Thank you.